Object Process Methodology. Object Process Methodology (OPM) is a conception modeling language and methodology for capturing knowledge and designing systems, specified as ISO/PAS 19450. Based on a minimal universal ontology of stateful objects and processes that transform them, OPM can be used to formally specify the function, structure, and behavior of artificial and natural systems in a large variety of domains. OPM was conceived and developed by Dov Dori. The ideas underlying OPM were published for the first time in 1995. Since then, OPM has evolved and developed. In 2002, the first book on OPM was published, and on December 15, 2015, after 6 years of work by ISO TC184/SC5, ISO adopted OPM as ISO/PAS 19450. A second book on OPM was published in 2016. Since 2019, OPM has become a foundation for a professional certificate program in Model-Based Systems Engineering MBSE at edX. Lectures are available as web videos on YouTube. Overview. Object Process Methodology (OPM) is a conceptual modeling language and methodology for capturing knowledge and designing systems. Based on a minimal universal ontology of stateful objects and processes that transform them, OPM can be used to formally specify the function, structure, and behavior of artificial and natural systems in a large variety of domains. Catering to human cognitive abilities, an OPM model represents the system under design or study by modelling in both graphics and text for improved representation, understanding, communication, and learning. In Opm, an object is a thing that exists, or might exist physically or informatically. Objects are stateful. They may have states, such that at each point in time, the object is at one of its states or in transition between states. A process is a thing that transforms an object by creating or consuming it, or by changing its state. OPM is bimodal. It is expressed both visually/graphically in object process diagrams (OPD) and verbally/textually in object process language (OPL), a set of automatically generated sentences in a subset of English. A patented software package called OPCAT for generating OPD and OPL is freely available. History. The shift to the object-oriented OO paradigm for computer programming languages, which occurred in the 1980s and 1990s, was followed by the idea that programming should be preceded by object-oriented analysis and design of the programs, and, more generally, the systems those programs represent and serve. Thus, in the early 1990s, over 30 object-oriented analysis and design methods and notations flourished. Around that time, in 1991, Dov Dori, who then joined the Kenyan Israel Institute of Technology as faculty, realized that just as the procedural approach to software was not necessarily the most adequate one, neither was the pure OO approach, which puts objects as the sole first-class citizens, with methods or services. When he and colleagues from University of Washington were trying to model a system for automated transformation of engineering drawings to CAD models, he realized that not all the boxes in their model were really objects. Some were things that happened to objects. When he circled those things, a bipartite graph emerged, in which the nodes representing objects, the things that exist, were mediated by those circled nodes, which were identified as processes, the things that transform the objects. Dori published the first paper on OPM in 1995. In 1997, the methods were culminated in the adoption of the Unified Modeling Language (UML) by the Object Management Group (OMG), making it the de facto standard for software design. UML 1.1 was submitted to the OMG in August 1997 and adopted by the OMG in November 1997. UML 1.x had 9 types of diagrams. Following a 2001 initiative of the International Council on Systems Engineering in COS. In 2003, OMG issued the UML for Systems Engineering Request for Proposals, and in 2006 OMG adopted SysML Systems Modeling Language 1.0 specification, which is based on UML 2. Since then, SysML has become the de facto standard for systems engineering. The first book on OPM, Object Process Methodology, a Holistic Systems Paradigm, was published in 2002, and OPM has since been applied in many domains, ranging from the semantic web to defense and to molecular biology. The recognition that models can and should become the central artifact in system life cycles has been gaining momentum in recent years, giving rise to model-based systems engineering MBSE as an evolving field in the area of systems engineering. SysML and OPM have been serving as the two MBSE languages, but since SysML was adopted as a standard about 8 years before OPM and has been backed by top-notch vendors, its adoption is currently more widespread. However, OPM is rapidly gaining acceptance in academia and industry. In August 2014, after 5 years of work by ISO TC184/SC5, a second book on OPM, which also covers SysML, was published in 2016. Design. Object Process Methodology (OPM) is a systems modeling paradigm that integrates two aspects inherent in any system: its structure and its behavior. Structure is represented via objects and structural relations among them, such as aggregation, participation, whole-part relation, and generalization. Specialization is a relation. Behavior is represented by processes and how they transform objects, how they create or consume objects, or how they change the states of an object. Indeed, OPM is fundamentally simple. It builds on a minimal set of concepts: stateful objects, things that exist or might exist physically or informatically at some state, and processes, things that happen to objects and transform them by creating or consuming the objects or by changing their states. 2. OPM offers a way to model systems of almost any domain, be it artificial or natural. OPM has an ontological commitment to a universal minimal ontology according to which objects exist, while processes transform them. X transformation includes object creation and consumption, as well as change of the state of an object. Hence, stateful objects and processes that transform them are the only two concepts in OPM universal minimal ontology. Two other cornerstones of OPM are its bimodal graphical textual representation. Modeling. OPM represents the system model simultaneously in two different modalities: object process diagrams (OPD) and a corresponding set of sentences in a subset of English called Object Process Language (OPL). OPL is generated automatically by OPET, a software tool that supports modeling in OPM. Object Process Diagram (OPDOP) is the one and only kind of diagram of OPM. This uniqueness of diagram kind is a major contributor to OPM's simplicity, and it is in sharp contrast to UML, which has 14 kinds of diagrams, and to SysML, which has 9 such kinds. And OPD graphically describes objects, processes, and links among them. Links can be structural and procedural. Structural links connect objects or processes to processes, expressing the static system aspect, how the system is structured. Procedural links connect objects to processes, expressing the dynamic system aspect, how the system changes over time. The entire system is represented by a set of hierarchically organized OPD such that the root OPD, called the systems diagram SD, specifies the bird's eye view of the system, and lower-level OPD specify the system. All the OPD in the system's OPD set are aware of each other, with each showing the system or part of it at some level of detail. The entire system is specified in its entirety by the union of the details model facts appearing in all the OPD. Object Process Language (OPL). Each OPD construct, i.e. two or more things connected by one or more links, is translated to a sentence in OPL, a subset of natural English. The power of OPL lies in the fact that it is readable by humans, but also interpretable by computers. Since each model fact is expressed both graphically and textually in a subset of natural English, it is readily accessible to non-technical stakeholders, enabling them to take part in the early, critical stages of the system requirements, elicitation, architecting, and development. These are the stages where the most important design decisions are made. The graphics text bimodality of OPM makes it suitable to jointly model requirements by a team that involves both the customer or his domain expert on one hand, and the system architect, modelers, and designers on the other hand. 3. OPM model animated simulation. OPM models are not just static graphical and textual representations of the system, they are also executable. A correct OPM model constructed in OPM can be simulated by animating it, visually expressing how the system behaves over time to achieve its function at all detail levels. An incorrect OPM model will not execute all the way through and will indicate where and why it is stuck, effectively serving as a visual debugger. Development. In his foreword to Dori's book Model-Based Systems Engineering with OPM and SysML, Edward F. Crawley said, OPM semantics was originally geared towards systems engineering, as it can model information hardware, people, and regulation. However, in recent years, OPM started to serve also researchers in molecular biology, yielding new published findings related to the mRNA life cycle. This is a clear indication of the universality of the object and process ontology. Romans 6. Basics. OPM has two main parts, the language and the methodology. The language is by model. It is expressed in two complementary ways: modalities. The visual, graphical part, a set of one or more object process diagrams OPD, and a corresponding textual part, a set of sentences in object process language OPL, which is a subset of English. The top-level OPD is the system diagram SD, which provides the context for the system's function. For man-made systems, this function is expected to benefit a person or a group of people, the beneficiary. The function is the main process in SD, which also contains the objects involved in this process, the beneficiary, the operand, the object upon which the process operates, and possibly the attribute whose value the process changes. OPM graphical elements are divided into entities, expressed as closed shapes, and relations, expressed as links that connect entities. Entities are the building blocks of OPM. They include objects and processes, collectively called things, and object states. An object is a thing which, once constructed, exists or can exist physically or informatically. Associations among objects constitute the object structure of the system being modeled. In OPL text, the object name shall appear in boldface with capitalization of each word. Object state. An object state is a particular situation classification of an object at some point during its lifetime. At every point in time, the object is in one of its states or in transition between two of its states from its input state to its output state. Process. A process is an expression of the pattern of transformation of objects in the system. A process does not exist in isolation. It is always associated with and occurs or happens to one or more objects. A process transforms objects by creating them, consuming them, or changing their state. Thus, processes complement objects by providing the dynamic, behavioral aspect of the system. In OPL text, the process name shall appear in boldface with capitalization of each word. Links. Structural link. A structural link defines a structural relation. A structural relation shall specify an association that persists in the system for at least some interval of time. Procedural link. A procedural link defines procedural relation. A procedural relation shall specify how the system operates to attain its function, designating time-dependent or conditional triggering of processes which transform object. Event and condition. The event condition action paradigm provides the OPM operational semantics and flow of control. An event is a point in time at which an object is created or appears to be created from the system's perspective, or an object enters a specified state. At runtime, this process triggering initiates evaluation of the process precondition. Thus, starting a process execution has two prerequisites: one, a triggering event, and two, satisfaction of a precondition. Once the event triggers a process, the event ceases to exist. The precondition is the existence of the required object instances in the preprocess object set, possibly in specific states, as modeled. If and only if the evaluation reveals satisfaction of the precondition, the process starts executing. Syntax and semantics. Things. An OPM thing is a generalization of object and process. Objects and processes are symmetric in many regards and have much in common in terms of relations, such as aggregation, generalization, and characterization. OPM objects and OPM processes depend on each other in the sense that an object cannot be transformed without a process, while a process cannot happen without transforming at least one object. To apply OPM in a useful manner, the modeler has to make the essential distinction between objects and processes as a prerequisite for successful system analysis and design. By default, a noun shall identify an object. Thing generic attributes. OPM things have the following three generic attributes. Perseverance, which pertains to the thing's persistence and determines whether the thing is static, i.e. an object, or dynamic, i.e. a process. Essence, which pertains to the thing's nature and determines whether the thing is physical or informatical. Accordingly, the values of the generic attribute essence are physical and informatical. Affiliation, which pertains to the thing's scope and determines whether the thing is systemic, i.e. part of the system, or environmental, i.e. part of the system's environment. Accordingly, the values of the generic attribute affiliation are systemic and environmental. Graphically, shading effects shall depict physical OPM things and dashed lines shall depict environmental OPM things. OPM thing generic attributes have the following default values. The default value of the affiliation generic attribute of a thing is systemic. System essence shall be the primary essence of the system. Like thing essence, its values are informatical and physical. Information systems in which the majority of things are informatical shall be primarily informatical, while systems in which the majority of things are physical shall be primarily physical. The default value of the essence generic attribute of a thing in a primarily informatical physical system shall be informatical physical. Object states. Stateful and stateless objects. An object state is a possible situation in which an object may exist. An object state has meaning only in the context of the object to which it belongs. A stateless object shall be an object that has no specification of states. A stateful object shall be an object for which a set of permissible states are specified. In a runtime model, at any point in time, any stateful object instance is at a particular permissible state or in transition between two states. Attribute values. An attribute is an object that characterizes a thing. An attribute value is a specialization state in the sense that a value is a state of an attribute. An object has an attribute, which is a different object to which that value is assigned for some period of time during the existence of the object exhibiting that attribute. Object state representation. A state is graphically defined by a labeled, rounded corner rectangle placed inside the owning object. It cannot live without an object. In OPL text, the state name shall appear in boldface without capitalization. Initial, default, and final states. The initial state of an object is its state as the system starts executing, or its state upon generation by the system during execution. The final state of an object is its state as the system completes executing, or its state upon consumption by the system during execution. The default state of an object is its expected state, the state in which the object is most likely to be when randomly inspected. An object can have 0 or more initial states, 0 or more final states, and 0 or 1 default state. Initial, final, and default state representation. A state that is initial is graphically defined by a state representation with thick contour. A state that is final is graphically defined by a state representation with double contour. A state that is default is graphically defined by a state representation with an open arrow pointing diagonally from the left. The corresponding OPL sentences shall include explicit indicators for an initial, final, or default state. Links. Procedural links. A procedural link is one of three kinds. Transforming link, which connects a transformer and object that the process transforms or its state with a process to model object transformation, namely generation, consumption, or state change of that object as a result of the process execution. Enabling link, which connects an enabler and object that enables the process occurrence but is not transformed by that process or its state to a process which enables the occurrence of that process. Control link, which is a procedural transforming or enabling link with a control modifier, the letter E for event or C for condition, which adds semantics of a control element. The letter E signifies an event for triggering the linked process, while the letter C signifies a condition for execution of the linked process or connection of two processes denoting invocation or exception. Procedural link uniqueness OPM principle. A process needs to transform at least one object. Hence, a process shall be connected via transforming link to at least one object or object state. At any particular extent of abstraction, an object or any one of its states shall have exactly one role as a model element with respect to a process to which it links. The object may be a transformee or an enabler. Additionally, it can be a trigger for an event if it has the control modifier E, or a conditioning object if it has the control modifier C, or both. According to the procedural link uniqueness OPM principle, at a given extent of abstraction, an object or an object state shall link to a process by only one procedural link. State-specified procedural links. Each procedural link may be qualified as state-specified procedural links. A state-specified procedural link is a detailed version of its procedural link counterpart in that rather than connecting a process to an object, it connects a process to a specific state of that object. Transforming links. A transforming link specifies a connection between a process and its transformee, the object it creates, consumes, or changes the object state. The three kinds of transforming links are consumption link, a transforming link specifying that the linked process consumes, destroys, eliminates the linked object, the consumee. Existence of the consumee is precondition or part of the precondition to the activation of the process. Graphically, an arrow with a closed arrowhead pointing from the consumee to the consuming process defines the consumption link. By assumption, the consumed object disappears as soon as the process begins execution. The syntax of a consumption link OPL sentence is processing consumes consumee. Effect link, a transforming link specifying that the linked process affects the linked object, which is the effectee, i.e., the process causes some unspecified change in the state of the effectee. Graphically, a bidirectional arrow with two closed arrowheads, one pointing in each direction between the affecting process and the affected object, shall define the effect link. The syntax of an effect link OPL sentence is processing effects effectee. Result link, a transforming link specifying that the linked process creates, generates, yields the linked object, which is the resultee. Graphically, an arrow with a closed arrowhead pointing from the creating process to the resultee shall define a result link. The syntax of a result link OPL sentence is processing yields resultee. Enabling links. An enabling link is a procedural link specifying an enabler for a process and object that must be present for that process to occur, but the existence and state of that object after the process is complete are the same as just before the process began. The two kinds of enabling links are agent and agent link. a human or a group of humans capable of intelligent decision-making who enable a process by interacting with the system to enable or control the process throughout execution. It is an enabling link specifying that the agent object is necessary for the linked process to execute. Graphically, a line with a filled circle black lollipop at the terminal end extending from the agent object to the process it enables defines an agent link. The syntax of an agent link OPL sentence is: agent handles processing. Instrument and instrument link, an inanimate or otherwise non-decision-making enabler of a process that cannot start or take place without the existence and availability of the instrument. It is an enabling link specifying that the instrument object is necessary for the linked process to execute. Graphically, a line with an open circle white lollipop at the terminal end extending from the instrument object to the process it enables defines an instrument link. The syntax of an instrument link OPL sentence is: processing requires instrument. State-specified transforming links. A state-specified transforming link connects one of the transformee states to or from that process. State-specified consumption link. A consumption link that originates from a particular state of the consumee, meaning that the consumee must be in that state for it to be consumed by the process to which it is linked. Graphically, an arrow with a closed arrowhead pointing from the particular object state to the process which consumes the object defines the state-specified consumption link. The syntax OPL sentence is: process consumes qualified state object. State-specified result link, a result link that terminates at a specific state of the resultee, meaning that the resultee shall be in that resultant state upon its construction. Graphically, an arrow with a closed arrowhead pointing from the process to the particular object state defines the state-specified result link. The syntax OPL sentence is: process yields qualified state object. State-specified effect links. Input and output effect links. An input link is the link from the object's input state to the transforming process, while the output link is the link from the transforming process to the object's output state. Input-output specified effect link, a pair of effect links, where the input link originates from a particular state of the effectee and the output link originates from that process and terminates at the output state of the same effectee. Graphically, a pair of arrows with a closed arrowhead from the input state of the effectee to the affecting process and a similar arrow from that process to the state of the effectee at process terminates defines the input-output specified effect link. The syntax OPL sentence is: process changes object from input state to output state. Input specified effect link, a pair of effect links, where the input link originates from a particular state of the effectee and the output link originates from that process and terminates at the effectee without specifying a particular state. Graphically, a pair of arrows consisting of an arrow with a closed arrowhead from a particular state, the input state of the effectee, to the process, and a similar arrow from that process to the effectee, but not to any one of its states, defines the input specified effect link. The syntax OPL sentence is: process changes object from input state. Output specified effect link, a pair of effect links, where the input source link originates from an effectee and the output link originates from the process and terminates at the output destination, resultant state of the same effectee. Graphically, a pair of arrows consisting of an arrow with a closed arrowhead from the effectee, but not from any one of its states, to the affecting process, and a similar arrow from that process to a particular state of that effectee, the output state, defines the output specified effect link. The syntax OPL sentence is: process changes object to output state. State-specified enabling links originate from a specific qualifying state and terminate at a process, meaning that the process may occur if and only if the object exists at the state from which the link originates. State-specified agent link, an agent link that originates from a specific qualifying state of the agent. Graphically, a line with a filled circle black lollipop at the terminal end extending from the qualifying state of the agent object to the process it enables defines a state-specified agent link. The syntax OPL sentence is: qualifying state agent handles processing. State-specified instrument link, an instrument link that originates from a specific qualifying state of the instrument. Graphically, a line with an empty circle white lollipop at the terminal end extending from the qualifying state of the instrument object to the process it enables defines a state-specified instrument link. The syntax OPL sentences processing requires qualifying state instrument. Event condition action control. For process object set and process precondition. In order for an OPM process to start executing once it has been triggered, it needs a set of objects comprising one or more consumes, some possibly at specific states, and / or effects, collectively called the preprocess object set. The pre-process object set determines the precondition that must be satisfied before execution of that process starts and is a condition for that process to start executing. At instance-level execution, each consume B in the pre-process object set of process P shall be consumed and stop to exist at the beginning of the lowest level subprocess of P which consumes B, each affected an object whose state changes B in the preprocess object set of process P shall exit from its input state at the beginning of the lowest level subprocess of P. Post-process object set and process post-condition. A set of objects comprising one or more results, some possibly at given states, and / or effects, collectively called the post-process object set, shall result from executing a process and carrying out the transformations associated with its execution. The post-process object set shall determine the post-condition, which shall be satisfied after execution of that process ends. Each resulted be in the post-process object set of process P shall be created and start to exist at the end of the lowest level subprocess of P which yields B. Each affected B in the post-process object set of process P shall enter its output state at the end of the lowest level subprocess of P. Control links. Structural links, slinks, role links. Structural links specify static, time-independent, long-lasting relations in the system. A structural link connects two or more objects or two or more processes, but not an object and a process, except in the case of an exhibition characterization link. Unidirectional tagged structural link as a user-defined semantics regarding the nature of the relation from one thing to the other. Graphically, an arrow with an open arrowhead. Along the tagged structural link, the modeler should record a meaningful tag in the form of a textual phrase that expresses the nature of the structural relation between the connected objects or processes and makes sense when placed in the OPL sentence whose. Unidirectional null tagged structural link. A unidirectional tagged structural link with no tag. In this case, the default unidirectional tag is used. The modeler has the option of setting the default unidirectional tag for a specific system or a set of systems. If no default is defined, the default tag is relates to. Bidirectional tagged structural link. When the tags in both directions are meaningful and not just the inverse of each other, they may be recorded by two tags on either side of a single bidirectional tagged structural link. Each tag shall align on the side of the arrow with the harpoon edge sticking out of the arrowhead unambiguously determining the direction in which each relation applies. The syntax of the resulting tagged structural link is two separate tagged structural link OPL sentences, one for each direction. Graphically, a line with harpoon-shaped arrowheads on opposite sides at both ends of the link's line shall. Reciprocal tagged structural link. A reciprocal tagged structural link is a bidirectional tagged structural link with no more than one tag. In either case, reciprocity indicate that the tag of a bidirectional structural link has the same semantics for its forward and backward directions. When no tag appears, the default tags shall be are related. The syntax of the reciprocal tagged structural link with only one tag shall be source thing and destination thing are reciprocity tag. The syntax of the reciprocal tagged structural link with no tag is source thing and destination thing are related. Fundamental structural relations. The most prevalent structural relations among OPM things and are of particular significance for specifying and understanding systems. Each of the fundamental relations is elaborate or refined one OPM thing, the source thing or refiné, into a collection of one or more OPM things, the destination thing or things, or refinables. The fundamental structural relations are aggregation, exhibition characterization, generalization specialization, and classification instantiation. Aggregation participation link. A riffany, the whole aggregates one or more other rifinables the parts. Graphically, a black solid filled in triangle with its apex connecting by a line to the whole and the parts connecting by lines to the opposite horizontal base shall denote the aggregation participation relation link. Exhibition characterization link. A thing exhibits or is characterized by another thing. The exhibition characterization relation binds a riffany the exhibitor with one or more rifinables, which shall identify features that characterize the exhibitor graphically, a smaller black triangle inside a larger empty triangle, with that larger triangle's apex connecting by a line to the exhibitor, and the features connecting to the opposite horizontal base. Generalization, specialization, and inheritance. These are structural relations which provide for abstracting any number of objects or process classes into superclasses and assigning attributes of superclasses to subordinate classes. Generalization specialization link. The riffany, the general generalizes the riffinables, which are specializations of the general. Binds one or more specializations with the same persistence attribute value as the general such that either the general and all its specializations are objects or the general and all its specializations are processes. Graphically, an empty triangle with its apex connecting by a line to the general and the specializations connecting by lines to the opposite base defines the generalization specialization link. Inheritance through specialization. Inheritance is assignment of OPM elements of a general to its specializations. A specialization inherits from the general thing through the generalization specialization link the following four kinds of inheritable elements, if there are any. 1. All the general's parts from its aggregation participation link. 2. All the general's features from its exhibition characterization link. 3. All the tagged structural links to which the general connects, and 4. All the procedural links to which the general connects. Specialization restriction. Through discriminating attribute, a subset of the possible values of an inherited attribute may restrict the specialization. An attribute whose different values determine corresponding specializations is a discriminating attribute. Classification instantiation and system execution. The relation between a class of things and an instance of that class in the system at the operational level. Classification instantiation link. A source thing, which is an object class, or a process class connect to one or more destination things which are valued instances of the source thing's pattern, i.e. the features specified by the pattern acquire explicit values. This relation provides the modeler with an explicit mechanism for expressing the relationship between a class and its instances created by the provision of feature values. Graphically, a small black circle inside an otherwise empty larger triangle, with apex connecting by a line to the class thing and the instance things connecting by lines to the opposite base defines the classification instantiation relation link. The syntax is instance thing is an instance of class thing. Instances of object class and process class. These are two distinct kinds of classes. An instance of a class is an incarnation of a particular identifiable instance of that class, an actual object of some class of objects bearing the same classification identifier. A single actual object is an object instance, while the pattern of object, which all the instances follow, is an object class. A process class is a pattern of happening, which involves object classes that are members of the preprocess and post-process object sets. A single actual process occurrence, which follows this pattern and involves particular object instances in its preprocess and post-process object sets, is a process instance. Hence, a process instance is a particular occurrence of a process class to which that instance belongs. Any process instance have associated with it a distinct set of preprocess and post-process object instance sets. State-specified structural relations and links. These provide for associating a state of one object with another object or with a state of another object. State-specified characterization relation and link, an exhibition characterization relation from a specialized object that exhibits a value for a discriminating attribute of that object, meaning that the specialized object shall have only that value. Graphically, the exhibition characterization link triangular symbol with its apex connecting to the specialized object and its opposite base connecting to the value defines the state-specified characterization relation. The syntax is specialized object exhibits value name attribute name. State-specified tagged structural relations and links, a structural relation between a state of an object or value of an attribute and another object or its state or value, meaning that these two entities are associated with the tag expressing the semantics of the association. In case of a null tag, i.e., the tag is not specified, the corresponding default null tag is used. Three groups of state-specified tagged structural relations exist: one source state-specified tagged structural relation, two destination state-specified tagged structural relation, three source and destination state-specified tagged structural relation. Each of these groups includes the appropriate unidirectional, bidirectional, and reciprocal tagged structural relation, giving rise to 7 kinds of state-specified tagged structural relation link and corresponding OPL sentences. More information and examples can be found in Model-Based Systems Engineering with OPM and SysML, Chapter 3.3, Adding Structural Links. Relationship cardinalities. Object multiplicity in structural and procedural links. Object multiplicity shall refer to a requirement or constraint specification on the quantity or count of object instances associated with a link. Unless a multiplicity specification is present, each end of a link shall specify only one thing instance. The syntax of an OPL sentence that includes an object with multiplicity shall include the object multiplicity preceding the object name, with the object name appearing in its plural form. Multiplicity specifications may appear in the following cases: to specify multiple source or destination object instances for a tagged structural link of any kind, to specify a participant object with multiple instances in an aggregation participation link, where a different participation specification may be attached to each one of the parts of the whole, to specify an object with multiple instances in a procedural relation. Object multiplicity expressions and constraints. Object multiplicity may include arithmetic expressions which shall use the operator symbols plus, asterisk, slash, and with their usual semantics, and shall use the usual textual correspondence in the corresponding OPL sentences. An integer or an arithmetic expression may constrain object multiplicity. Graphically, expression constraints shall appear after a semicolon separating them from the expression that they constrain and shall use the equality/inequality symbols equals, and equals, the curly braces and for enclosing set members, and the membership operator in element of, all with their usual semantic. The corresponding OPL sentence shall place the constraint phrase in bold letters after the object to which the constraint applies in the form where constraint. Attribute value and multiplicity constraints. The expression of object multiplicity for structural and procedural links specifies integer values or parameter symbols that resolve to integer values. In contrast, the values associated with attributes of objects or processes may be integer or real values or parameter symbols that resolve to integer or real values, as well as character strings and enumerated values. Graphically, a labeled, rounded corner rectangle placed inside the attribute to which it belongs shall denote an attribute value, with the value or value range integers, real numbers, or string characters corresponding to the label name. In OPL text, the attribute value shall appear in boldface without capitalization. The syntax for an object with an attribute value OPL sentence shall be attribute of object is value. The syntax for an object with an attribute value range OPL sentence shall be attribute of object range is value range. A structural or a procedural link connecting with an attribute that has a real number value may specify a relationship constraint which is distinct from an object multiplicity. Graphically, an attribute value constraint is an annotation by a number, integer or real or a symbol parameter, near the attribute end of the link and aligning with the link. Logical operators and, SOR, and OR, and OR, and OR, and OR, and OR, and OR, and OR. Logical and procedural links. The logical operators and XOR and or among procedural relations enable specification of elaborate process precondition and postcondition. Separate non-touching links shall have the semantics of logical and. In the example, opening the safe requires all three keys. Logical XOR and or procedural links. A group of two or more procedural links of the same kind that originate from or arrive at the same object or process shall be a link fan. A link fan shall follow the semantics of either a XOR or and or operator. The link fan end that is common to the links shall be the convergent link end. The link end that is not common to the links shall be the divergent link end. The XOR operator shall mean that exactly one of the things in the span of the link fan exists if the divergent link end has objects, or happens if the divergent link end has processes. Graphically, a dashed arc across the links in the link fan with the arc focal point at the convergent and point of contact shall denote the XOR operator. The OR operator shall mean that at least one of the two or more things in the span of the link fan exists if the divergent link end has objects, or happens if the divergent end has processes. Graphically, two concentric dashed arcs across the links with their focal point at the convergent and point of contact shall denote the OR operator. State-specified XOR and or link fans. Each one of the link fans in shall have a corresponding state-specified version where the source and destination may be specific object states or objects without a state specification. Combinations of state-specified and stateless links as destinations of a link fan may occur. Control modified link fans. Each one of the XOR link fans for consumption, result, effect, and enabling links and their state-specified versions shall have a corresponding control modified link fan, an event link fan, and a condition link fan. The example presents the event and condition effect link fans as representatives of the basic non-state specified links version of the modified link fans. Link probabilities and probabilistic link fans. A process P with a result link that yields a stateful object B within states sown through S and shall mean that the probability of generating B at each one of its states shall be 1/n. The single result link shall be used instead of the result link fan. Usually, probabilities of following a specific link in a link fan are not equal. Link probability shall be a value assigned to a link in an XOR diverging link fan that specifies the probability of following that particular link among the possible links in the fan link. A probabilistic link fan shall be a link fan with probability annotations on each fan link, where the sum of the probabilities shall be exactly 1. Graphically, along each fan link an annotation shall appear in the form PR equals P, where P is the link probability numeric value or a parameter which denotes the probability of the system control to select and follow that particular link of the fan. The corresponding OPL sentence shall be the XOR diverging link fan sentence without link probabilities, omitting the phrase exactly one of, and the phrase with probability P following each thing's name with a probability annotation PR equals P. Execution path and path labels. A path label shall be a label along a procedural link, which, in the case that there is more than one option to follow upon process termination, prescribes that the link to follow will be the one having the same label as the one which we entered the process. A path label is a label on a procedural link that removes the ambiguity arising from multiple outgoing procedural links by specifying modeling principles and model comprehension. System function and modeling purpose is to guide the scope and level of detail of an OPM model. The definition of system purpose, scope, and function in terms of boundary, stakeholders, and preconditions is the basis for determining whether other elements should appear in the model. This determines the scope of the system model. OPM provides abstracting and refining mechanisms to manage the expression of model clarity and completeness. The model has a hierarchy tree for refinement, elaboration, or decomposition obtained by unfolding. Stakeholder and systems beneficiary identification. In order to start an OPM model of a system, the first step is to determine the function of the system, the main process of the system. A beneficiary of the artificial, man-made system is a stakeholder who receives functional value and benefits from the function of the system. For man-made systems, this function is expected to benefit a person or a group of people, the beneficiary. After the function of the system aligns with the functional value expectation of its main beneficiary, the modeler identifies and adds other principal stakeholders to the OPM model. Modeling a system starts by defining, naming, and depicting the function of the system, which is also its top-level process. System diagram. The resulting top-level OPD is the system diagram SD, which includes the stakeholder group, in particular the beneficiary group, and additional top-level environmental things, which provide the context for the system's operation. The SD should contain only the central and important things, those things indispensable for understanding the function and context of the system. The function is the main process in SD, which also contains the objects involved in this process, the beneficiary, the operand, the object upon which the process operates, and possibly the attribute of the operand, whose value the process changes. An OPM model fact needs to appear in at least one OPD in order for it to be represented in the model. SD should also contain an object representing the system that enables the function. The default name of this system is created by adding the word system to the name of the function. For example, if the function is car painting, the name of the system would be car painting system. OPD tree. SD is always the only top-level OPD. It is the root of the OPD tree. The set of OPD organized as a process tree, which together specify the system. The OPD set keeps growing as additional OPD are gradually constructed to increasingly refine the model and make it more concrete. The ability to add a descendant subordinate OPD whenever the one currently under work reaches its congestion limits makes it possible to avoid overcluttering any single OPD. Clarity and completeness. Trade-off. Clarity is the extent of unambiguous comprehension the system's structure and behavior models convey. Completeness is the extent of specification for all the system's details. These two model attributes conflict with each other. On the one hand, completeness requires the full stipulation of system details. On the other hand, the need for clarity imposes an upper limit on the extent of detail within an individual model diagram, after which comprehension deteriorates because of clutter and overloading. Establishing an appropriate balance requires careful management of context during model development. However, the modeler may take advantage of the union of information provided by the entire OPD set of an OPM system model and have one OPD which is clear and unambiguous but not complete, and another that focuses on completeness for some smaller part of the system by adding more details. Refinement abstraction mechanisms. OPM shall provide abstracting and refining mechanisms to manage the expression of model clarity and completeness. These mechanisms make possible the specification of contextualized model segments as separate yet interconnected OPD which, taken together, shall provide a model of the functional value providing system. These mechanisms shall enable presenting and viewing the system and the things that comprise it in various contexts that are interrelated by the objects, processes, and relations that are common amongst them. Explicitly depicting the states of an object in an OPD may result in a diagram that is too crowded or busy, making it hard to read or comprehend. The OPM refinement abstraction mechanisms shall be the following pairs of inverse operations: state expression and suppression, unfolding and folding, and inzooming and outzooming. State expression and state suppression. OPM shall provide an option for state suppression, i.e., suppressing the appearance of some or all the states within an object as represented in a particular OPD when those states are not necessary in that OPD context. The inverse of state suppression shall be state expression, i.e., refining the OPD by adding the information concerning possible object states. The OPL corresponding to the OPD shall express only the states of the objects that are depicted. Unfolding and folding. Unfolding is a mechanism for refinement, elaboration, or decomposition. It reveals a set of things that are hierarchically below the unfolded thing. The result is a hierarchy tree, the root of which is the unfolded thing. Linked to the root are the things that constitute the context of the unfolded thing. Conversely, folding is a mechanism for abstraction or composition which applies to an unfolded hierarchical tree. Inzooming and outzooming. Inzooming is a kind of unfolding which is applicable to aggregation participation only and has additional semantics. For processes, inzooming enables modeling the subprocesses, their temporal order, their interactions with objects, and passing of control to and from this context. For objects, inzooming creates a distinct context that enables modeling the constituent object's spatial or logical order. Graphically, the timeline within the context of an inzoomed process flows from the top of its process ellipse symbol to the ellipse bottom. Metamodeling. A metamodel is a model of a model, in particular using OPM model to present aspects of OPM. The examples described here are a part of the comprehensive metamodels of OPM appear in an annex of ISO 19450. OPM Model Structure. OPM model is a metamodel as shown in the image of OPM model on the right. Using OPM to specify the structure of an OPM model of a system. It depicts the conceptual aspects of OPM as parallel hierarchies of the graphic and textual OPM modalities and their correspondence to produce equivalent model expressions. An OPD construct is the graphical expression of the corresponding textual OPL sentence, which express the same model fact. An OPD and its corresponding OPL paragraph are collections of model facts that a modeler places into the same model context. Model of OPD construct and basic construct. The model, as seen in the image of OPD metamodel, elaborates the OPD construct concept. The purpose of this model is to distinguish basic construct from another possible OPD construct. A basic construct is a specialization of OPD construct which consists of exactly two things connected by exactly one link. The non-basic constructs include, among others, those with link fans or more than two refinees. A modeler could add a process to the model by adding states disconnected and connected of thing set. The purpose of the model thus includes the action of transforming a disconnected thing set to a connected thing set using the link set as an instrument of connection. OPM model of thing. OPM model of thing is a model for an OPM thing, showing its specialization into object and process, as depicted in the image of model of thing below. A set of states characterize object, which can be empty in a stateless object, or non-empty in the case of a stateful object. A stateful object with S states gives rise to a set of S stateless state-specific objects, one for each state. A particular state-specific object refers to an object in a specific state. Modeling the concept of state-specific object as both an object and a state enables simplifying the conceptual model by referring to an object and any one or its states by simply specifying object. OPM model of thing generic properties. OPM model of thing generic properties depicts thing and its perseverance, essence, and affiliation. Generic properties modeled as attribute refinees of an exhibition characterization link. Perseverance is the discriminating attribute between object and process. Essence is the discriminating attribute between physical object and physical process on the one hand, informatical object, and informatical process on the other hand. Affiliation is the discriminating attribute between systemic object and systemic process on the one hand, environmental object, and environmental process on the other hand. In zooming and outzooming models, both new diagram, in-zooming and new diagram, out-zooming create a new OPD context from an existing OPD context. New diagram, in-zooming starts with an OPD of relatively less details and adds elaboration or refinement. New diagram, zooming starts with an OPD of relatively more details and removes elaboration or refinement to produce a less detailed, more abstract thing in an ancestor context. New diagram, in zooming elaborates a refinable present in an existing OPD, say SDN, by creating a new OPD, SDN plus 1, which elaborates the refinable by adding subprocesses, associated objects, and relevant links. The new diagram in zooming and a new diagram out zooming processes are inverse operations. New diagram in zooming and new diagram out zooming models depict the new diagram in zooming and new diagram out zooming processes. The model on the right uses in diagram in zooming of the model on the left to elaborate the two processes, one for creating a new diagram in zoomed context and one for creating a new diagram out zoomed context. New diagram in zooming begins with content showing, followed by link refining. New diagram, out-zooming begins with link abstracting, the inverse process of link refining, followed by content hiding, the inverse process of content showing. Versions. OPM, the current version of OPM is ISO/PAS 19450, 2015 as specified in Automation Systems and Integration Object Process Methodology. The specification in Dori's 2016 book is a superset of ISO/PAS 19450 2015. The previous version of OPM was specified in Dori's 2002 book. The current OPET version is 4.1. It is available freely from Technian's Enterprise Systems Modeling Laboratory. A previous OPET version, 3.1, with fewer capabilities, is also available from the same site. Both are coded in Java. The first OPET version, OPET 1.x, was written in Visual C++ in 1998. In the beginning of 2016, a team of students under the management of Dori began working on the new generation of OPET, which will be called OP Cloud. As suggested by the name of the software, it will be a cloud-based application and will enable users to create OPM models using a web-based application. Standardization. ISO, the International Organization for Standardization, is an independent, non-governmental international organization with a membership of 162 national standards bodies, which develops voluntary, consensus-based, market-relevant international standards that support innovation and provide solutions to global challenges. These standards provide world-class specifications for products, services, and systems to ensure quality, safety, and efficiency. ISO and Opm. In June 2008, Richard Martin approached Dov Dori after his presentation at the INCOS International Symposium in Utrecht, the Netherlands, to inquire about the possibility of creating an international standard for OPM. Martin, convener of ISO TC184/SC5/W GON for Automation Systems Interoperability Architecture and Modeling, had for some time been searching for methodologies offering more than static information and process modeling. He provided Dori with a simple example to model that could demonstrate both the modeling capability of OPM and its dynamic simulation opportunity. In May 2010, Dori presented a brief overview of OPM and his demonstration model at the ISO Technical Committee 184/Subcommittee 5 TCON 184/SC5 plenary meeting, which then adopted a resolution to create an OPM study group for the purpose of examining the potential for OPM. The OPM study group began its work in October 2010 and issued an interim report for the 2011 SC5 plenary. The report included several uses of OPM to model existing SC5 standards and led to an initial motivation for the standardization of OPM. This deficiency could be significantly reduced if the standards were model-based rather than text-based, and OPM offered a useful underlying modeling paradigm for this purpose. A final OPM study group report and a draft for a meta-model for model-based standards authoring document were delivered at the 2012 SC5 plenary. As the OPM study group effort progressed, it became obvious that OPM could also serve as a solid and comprehensive basis for model-based systems engineering MBSE and for modeling both natural and man-made systems. ISO 19450 document TCON 184/SC5/W GON participants received the first draft of the OPM PAS in September 2011 with 16 pages, 2 annexes and a bibliography for a total of 25 pages. Most of the content simply identified subclause headings and spaceholder graphics. By the 2012 SC5 plenary, the PAS draft included 10 full clauses describing OPM features and 6 annexes totaling 86 pages. One annex was an ENF-extended Backus-NOR form used to formally specify context-free languages, enabling parsing of programming languages specification for OPL and another detailed OPD graph grammar. To facilitate verification of the ENF specification, David Shorter wrote a script to evaluate consistency and completeness of the ENF statement set. Further effort to add meaningful examples and complete all of the identified sections resulted in a draft of 138 pages by the time of the 2013 SC5 plenary. Subsequently, the working draft was registered with the SC5 Secretariat as a committee draft for initial circulation to SC5 members. Because the SC5 resolution calling for the OPM specification indicated that the document was to be registered as a publicly available specification PAS, it would have only one acceptance ballot opportunity. In April 2014, the new work item proposal and revised committee draft for ISO/PAS 19450 was delivered to SC5 for consideration. By now, the committee draft was 98 pages plus front matter. In March 2015, ISO/PAS 19450 was formally published with a total of 162 pages by ISO on December 15, 2015, culminating a 6-year effort to provide the standardization community with a formal specification for a new approach to modeling that binds together graphics and textual representations. Opm vs. SysML and UML. Opm vs. SysML. OPM and SysML represent two different approaches to system modeling. SysML is defined as an extension of the Unified Modeling Language UML using UML profile mechanism. In SysML, up to 9 multiple models are used, which are independently derived and may not be completely consistent. In Opm, only one single model emerges. The need to integrate several kinds of models may be more complicated in OPM. In OPM, there is a combination between complex, the inherent fact that a system contains many parts interacting in multiple, often inexplicable ways, and complexity, the way a system model is presented through a certain modeling language and is perceived by a user. OPM, with its minimal ontology of stateful objects and processes, favorably responds to the challenge of reducing the complexity of the representation to the bare necessities without sacrificing accuracy and detail. Opm vs. UML. The differences between OPM and UML are highly perceivable during the analysis and design stages. While UML is a multi-model, OPM supports a single unifying structure behavior model. The crucial differences stem from the structure-oriented approach of UML, in which behavior is spread over 13 diagram types, a fact that inevitably invokes the model multiplicity problem. First, using the OPM approach enables to view at main diagram SD the main process, objects, and the connection between them. In addition, it is easy to understand what is the main system's benefit presented at the SD. In Opm, it's also easier to understand the main 3 aspects of the system: behavior, structure, and functionality contrary to UML, which describes these aspects with different types of diagrams. Database unfolding modeling contributes to the understanding of system and all details which is stored in the system. In addition, creating in-zooming enables simplifying the model. OPM requires extensive knowledge of systematic processes, such as how the system saved the path and gets decisions. Generating SysML views from an OPM model. While both languages aim at the same purpose of providing a means for general-purpose systems engineering, these languages take different approaches in realizing this goal. SysML is a profile of UML Unified Modeling Language. Therefore, it is possible to convert an OPM diagram to an UML or SysML diagram. The OPM to SysML translation is one-to-many in the sense that a single OPM element entity or link usually translates to several SysML elements that belong in different SysML diagram types. For example, an OPM process, which is defined as an entity that transforms, generates, consumes, or changes the state of an object, can be mapped to any subset of the following SysML entities: use case in a use case diagram, action in an activity diagram, state transition trigger in a state machine diagram. As OPM and SysML are two distinct and differently designed languages, not all the constructs in one language have equivalent constructs in the other language. The first type of diagram in UML that can be generated from an OPM diagram is the use case diagram, which is intended for modeling the usage of a system. The main elements comprising the use case diagram are actors, and use cases the entities along with the relationships links among them. Generation of a use case diagram from OPM is therefore based on environmental objects, the actors, and the processes the use case is linked to them. Figure 1 is an example of use case diagram generation of SD0. The figure shows the root OPM diagram. A. The corresponding OPL texts, B. And the created use case diagram. C. Figure 2 shows a STUM level of OPD from the same OPM model. A. And the generated use case diagram. B. The second type of diagram is the block definition diagram BDD, which defines features of blocks like properties and operations and relationships between blocks, such as associations and generalizations. Generating a BDD is based upon the systemic objects of the OPM model and their relationships, mainly structural relations to other model elements. The third type of diagram is activity diagrams, which are intended to specify flow. Key components included in the activity diagram are actions and routing flow elements. In our context, a separate activity diagram can be generated for each OPM process containing child subprocesses, i.e., a process which is zoomed in the OPM model. There are two kinds of user parameters that can be specified via the settings dialog. The first one deals with selection of the OPM processes. One option is to explicitly specify the required OPM processes by selection from a list. The alternative, which is the default option, is to start with the root OPDSD and go down the hierarchy. Here we reach the second parameter that is independent of the first one, which is the required number of OPD levels K to go down the hierarchy. In order to give the user control over the level of abstraction, the diagrams are generated up to K levels down the hierarchy. Each level will result in the generation of an additional activity diagram, which is a child activity subdiagram contained in the enclosing higher level activity. The default setting for this option is all levels down, i.e. K equals. Study of model comprehension. In order to assess and examine the effectiveness of the newly developed OPM to SysML algorithm and application, Dov Dori and Yarov Grobstein performed a controlled experiment which had two major goals. Since improved system comprehension was among the potential predicted benefits, they ventured to examine whether the additional SysML diagrams that had been generated automatically with their new application affected system model comprehension. They wished to test the quality of the auto-created diagrams mainly in terms of modeling errors and inconsistencies with the original OPM model from which they were generated. They carried out the experiment within a lecture of the course Enterprise Systems Modeling taught in 2008, testing the null hypothesis that there is no difference in comprehension level between the OPM-only model and the combined OPM and SysML model against the two-sided alternative that there is a difference. They rejected the null hypothesis in both cases. For both systems, the students' answers to comprehension questions relating the combined OPM and SysML models were significantly better than answers relating to OPM-only models. It seems that the additional diagrams were helpful in answering some of the questions more than the others. Only one question of 8 in each of the cases scored lower when the combined diagrams specification was used. The SysML diagram that seems to have the biggest added value is the block definition diagram BDD, which specifies system hierarchy and features of blocks like attributes and operations. The relatively high helpfulness of the BDD is evident from both the student's assessment of the contribution of this diagram type and from analysis of the scores in the individual questions in both systems. According to the results of the experiment, the use case diagram seems to have the least effect on system comprehension, and this is also in agreement with the student's assessment of the use case diagram type contribution. In between are the activity diagram and the state machine diagram, which appear to have a positive effect, albeit not as high as the effect of the BDD. As noted, the other goal of the experiment was to assess the quality of the OPM. In this regard, the students did not find any issues of errors, inconsistencies, or contradictions associated with the SysML diagrams, indicating that the application has achieved a high level of model-to-model translation fidelity. In the study, an algorithm for automatic SysML views generation from an OPM model was developed and applied. For each SysML view, a mapping scheme from OPM elements to SysML elements constitutes the foundation for the OPM to SysML subalgorithm and translation engine application. The mappings are partial and do not utilize all the available language elements. The software implementation was OPCAT, the OPM supporting modeling tool.